the unit 5. The unit 5 and the topics included in unit 5, that is the thermal physics, simple harmonic motion, nuclear physics, gravitational field, and cosmology. So these are the topics which will cover this unit 5. We'll start with the thermal physics. So start with the thermal physics, the concept of heat, the basic definitions. Heat, how we define heat, it is total energy of molecules and temperature is the average kinetic energy of molecules. So when we take average kinetic energy of the molecule, we call that as the temperature. The SI unit of the temperature is Kelvin, denoted by K, and SI unit of heat, because it is energy, so SI unit is joules, denoted by J. Then we define the term heat capacity. So what is the meaning of heat capacity? Basically, it is the amount of energy required to change the temperature of given substance by 1 degree centigrade or 1 Kelvin. So example, you're supplying heat energy. The energy which you supply is denoted by E. The initial temperature was 20 degrees. As you supply heat energy, the temperature will change from 20 to 21. So how much energy you are supplying to this material so that its temperature changes by 1 degree centigrade, and the change in the temperature of 1 degree centigrade is, or temperature change in degree centigrade is also same as temperature change in Kelvin. Because if I convert both of them, like example 21 is there, degree centigrade, I will convert into Kelvin, I will add 273. So when I add 273, so 273 plus 21, that will make 294. And 273 plus 20, that is 293. So 293 Kelvin, which is equivalent to 20 degree centigrade, and 294 Kelvin, which is equivalent to 21 degree centigrade. So how much energy we supply? So as you can see, when we supply energy, the temperature change, if there is 1 degree change in temperature, that is same as 1 degree change in 1 degree change in temperature, or the change of 1 Kelvin is equals to change of 1 degree centigrade or 1 degree Celsius. So energy which we supply to change the temperature by 1 degree centigrade, that energy is known as heat capacity. So energy required to change temperature of given mass by 1 degree centigrade or 1 Kelvin. We call that as heat capacity. And heat capacity, the temperature change here refers to it is amount of energy removed so that temperature drop by 1 degree centigrade, or amount of energy supplied so that temperature change by 1 degree centigrade. So the formula to calculate this, the heat capacity or thermal capacity, is equals to energy supplied or energy removed divided by change in temperature. Heat capacity or thermal capacity is denoted by capital letter C. Energy which we supply is denoted by E, or you can also represent by Q. And the temperature change is denoted by delta T or delta theta, both. So energy can be represented by E or Q, and the temperature change can be denoted by delta T or delta theta, both are acceptable. So SI unit of energy is joule, SI unit of temperature is Kelvin or degree centigrade. SI unit is Kelvin, so we can use joule per Kelvin or joule per degree centigrade. That is refers to heat capacity. But what is specific heat capacity? Specific heat capacity in which the mass is specified. So when we use the term specific heat capacity, so specific heat capacity means it is amount of energy required to change temperature of 1 kilogram object by 1 Kelvin or 1 degree centigrade. So that is refers to specific heat capacity. And if you want to calculate the specific heat capacity, so specific heat capacity is equals to energy divided by mass into temperature change. So if we are only finding for each kilogram, like example, we have 1 kilogram object, we supplied 700 joules so that its temperature changes from 15 degrees centigrade to 16 degrees centigrade. So amount of energy which we supply so that for each kilogram object the temperature change by 1 degree centigrade, that energy supplied is known as specific heat capacity. But if we don't have a 1 kilogram object, example, we have 5 kilogram object and we are supplying 2000 joules of energy so that its temperature is changing from 20 degrees centigrade to 22. If we need a specific heat capacity, so here the temperature change is 2 degrees centigrade, the mass is not 1 kilogram. So here 2000 is not the specific heat capacity. So 2000 is for 5 kilogram and for 2 degree change in temperature. But we need for each kilogram and for 1 degree change in temperature. So that's why the energy supplied is equals to 2000 divided by mass, which is 5, divided by change in temperature, that's equal to 2. So 2000 divided by 10. So when we solve this, it will come out 200 joules for each kilogram and for every 1 degree change in temperatures. SI unit is joule per kilogram Kelvin, but other unit can be degree centigrade. Is it clear? The specific heat capacity and the heat capacity. The formula to calculate the specific heat capacity, this is a word equation. So formula, it is denoted by a letter small c. Energy which we supply, that is denoted by E or small q. Mass is small, it is energy denoted by capital E or Q. Mass is denoted by small m, and temperature change delta theta or delta T. The SI unit is joule per kilogram Kelvin. Other unit can be joule per kilogram degree centigrade. So when we supply energy, what are the possibilities when we are supplying energy or when we are removing energy? So there are two possibilities. Two things can happen. Number one, the object might change. There might be a change in temperature, or there might be a change in the state, like solid changing into liquid, liquid change to gas, or opposite. So if you are supplying energy, the object might show a change in temperature. So energy which is supplied, energy which we supply, and if we want to calculate if there is a change in temperature, so the formula we use for heat capacity or specific heat capacity, so E is equals to Cm delta T, or E is equals to thermal capacity or specific heat capacity multiplied by change in temperature. These are the two formula. But if there is a change in state, so the energy which we supply, that is equals to mass into latent heat, L, M into L. What is L? L stands for latent heat. What is the meaning of this latent heat? The term latent heat means, or basically specific latent heat. The term specific latent heat means energy required to change state of 1 kilogram object, and we can change the state, like we can convert solid into liquid, or opposite, liquid can change back to solid, or a liquid, so solid can turn into liquid, or a liquid can turn into solid, or a liquid can change to gas, or a gas can change back to liquid. So when solid is converting into liquid, we call that as specific latent heat of fusion. That change is called a melting, but the energy which we require to convert 1 kilogram of solid into liquid, we call that as specific latent heat of fusion. If we want to convert 1 kilogram of liquid into gas or opposite, then we call that as vaporization. Only the difference in when solid is converting into liquid, you have to supply energy. But when liquid change back to solid, the energy will be removed. And opposite here, when liquid change to gas, so energy is supplied, and gas change to liquid, energy is removed as the particle coming closer to each other. So it is depending on the question that whether in a question there is a change in state or there is a change in temperature. Sometimes you have both. Like, for example, if I have, say, ice, which is at minus 8 degrees centigrade, the temperature, and I'm supplying heat energy to this ice. So when I'm supplying heat energy to this ice, so first what will happen? The first, there will be a change in the temperature. So -8 will change into 0. That's a change in temperature. And then what happened? Further supplying heat energy, it will cause a change in state. This solid will convert into liquid. So when temperature change is there and we want to find how much energy we are supplying at this point, if there's a change in temperature, so E is equals to Cm delta T. If there's a change in state, like solid is converting into liquid, so E is equals to M into LF, because it is a fusion, so subscript F will be there. If it is vaporization, then subscript B will be there. Sometime we are using electrical heaters to supply energy. So if we are using electrical heater, to supply the energy, in that case, the energy supplied is equals to power of the heater and the duration, the time for which the heater is used. But time should be in second. So these are the formulas which are related to heat, or whenever there's a change in state or change in temperature for the different states of matter. And according to law of heat exchange, so according to law of heat exchange, heat lost by hot object is equals to heat gained by cold object. So heat loss and heat gain will be same. So our energy always transfer from hot object to cold object. Example, we have a container which is filled with water and we add ice cubes to this water. Ice cubes, because they have low density compared to water, so they will float. So what happened? These ice cubes, because their temperature, like example, if it's not melting at a melting temperature, maybe -2, and originally in the beginning, the water was there at 30 degree. So water is a hot object, these ice cubes are the cold object, and when the heat energy transfer, this heat energy transfer from hot object to cold object. So heat lost by water will be equal to heat gained by the ice. But how to find the heat loss or heat gain? It depends on what is happening to the matter, whether there is a change in state or there is a change in temperature, or both are happening. But for water, what will happen? The water will cool down. So for water, there will be a change in temperature. So if there is a change in temperature, so energy heat lost by the water is equals to heat gained by the ice. For water, there will be a change in temperature, so it will be Cm delta T. C is a specific heat of water, M is a mass of water, and delta T is a change in temperature of water. But what about ice? Here I mentioned ice is at -2. So first, ice is at -2. If it's a pure ice, it will reach 0. So first there will be a change in temperature, then there will be a change in state. And whenever the state is changing, the temperature does not change because the energy is used to break the intermolecular forces. So for heat gained by the ice is used first to change the temperature of the ice and then to change or melt these ice. So first it will be specific heat of ice, mass of ice, and change in temperature of the ice. Plus, because the ice will melt, so that will be mass into latent heat of fusion of ice. So this will be the equation you will use in this case. Is it clear? This part? Then experiment to find the specific heat capacity. So experiment to find the specific heat capacity. The formula to calculate the specific heat capacity is equals to energy divided by mass into temperature change. But practically the energy, we are not using a Bunsen burner because of low efficiency. Most of the energy lost to the surrounding when you are using a Bunsen burner, and it is difficult to calculate the how much energy is used. So practically we are using the electrical heaters, and when we are using electrical heaters, the energy supplied by the heater is equals to power multiplied by time. So specific heat capacity is equals to power multiplied by time divided by mass into change in temperature delta T. And power, because we are using electrical heater, so electrical power is a product of voltage and current. So specific heat capacity, practically if we need voltage, we need current, we need how much time the heater is switched on, what is the mass, and the temperature change. Temperature change is calculated. To calculate a temperature change, we measure initial and final temperature. So the quantities which we will measure, the voltage, current, time, mass, and temperature change. The quantities we are measuring, so measuring initial temperature and final temperature. The apparatus which we use to measure voltage, current, time, mass, initial temperature, and the final temperature. So voltage, it is measured by voltmeter. Current is measured by an ammeter. Time is measured by a stopwatch. Mass is measured by balance. Initial temperature by thermometer. And final temperature also by thermometer. And we calculate the temperature change by the difference of the two values. So these are the things which we need or required to measure the specific heat capacity for any material. It can be a solid, it can be a liquid, or it can be a gas. So for voltage, voltmeter, current, ammeter, stopwatch for time, balance, and initial temperature and the final temperature, both are by thermometer. So if it is solid, you will measure the mass of solid and connect a heater, measure the voltage, current, and how long or how much time you switch on the heater, and tell delta T is the change in temperature. So before uh, the heat is supplied, you will measure the initial temperature, and after some time, like after 5 minutes or 3 minutes, you will measure its final temperature and use the formula to calculate specific heat capacity. Then for gases, the state of the matter in which the particles are far away and negligible force of attraction between the particles and moving randomly, continuously colliding with the surface or the wall, but they're not moving in a specific direction, they are moving randomly. So for gases, we define the volume, the term volume. What is the meaning of volume? The term volume means it is a space occupied by the gas molecules. So how much space the gas molecules occupy, that is known as the volume of the gas. So total space which they occupy. So because they take the shape of the container, so as they take the shape of the container, so we can simply say the volume of the gas is equal to the volume of the container. And these gas molecules, they are moving randomly. So if we say the volume of the gas increase, what is the meaning that volume of the gas increase? It means the spaces or the spacing between the molecules will increase. And if we say the gas is compressed, it means the space between the molecule will decrease, or the molecules come closer to each other. But the size of the molecule does not change. The size of the molecule remains same. Only thing what changes is the spacing or the intermolecular, the distance between the two molecules or the particles. So if the volume, we say volume decrease, so spacing, the intermolecular space will decrease. And when we say the volume increase, it means the intermolecular space or the distance between the gas molecule increases. The second thing, we define pressure. What is the meaning of the pressure? It is force exerted by gas molecules when collide with walls of container, or in terms of momentum, you can also explain this pressure. When gas molecules hit the wall, they change direction, which cause change in momentum. Because if the direction change, the even though the velocity is same, even though the speed is same, but the velocity changes. As the velocity change, there will be a change in momentum, which create force. Whenever there's a change in momentum, it cannot be done without a force, so it create a force act on unit area, which will create pressure. And how we can work out the pressure? The SI unit of the pressure is Pascal or Newton per meter square, but the other units are there: ATM, atmosphere, or millimeter of the mercury. So there are formulas to calculate the pressure exerted by the gas molecules that we will discuss in the gas laws. The third one is a temperature. What is the temperature? The temperature is defined as the average kinetic energy of the gas molecules. So the average of the kinetic energy of the gas molecules, what we call that as a temperature. If the temperature increase, the velocity or the speed at which the particles are moving, that will also increase. So when we take average of the energy of these gas molecules, we will get the temperature. So we can also say the kinetic energy and temperature are directly proportional. But to find the kinetic energy, the formula for kinetic energy is half mv square. But we do not substitute the velocity here. Why we are not substituting the velocity? Like, because the kinetic energy, the average kinetic energy, the gas molecule, if identical gas is there, so they will all have the same mass. So what I can do, I can take an average velocity or average speed here. So when I try to take an average velocity, so if we want to find the average velocity of the gas molecules, so example, these are the gas molecules. Because they are moving randomly, if I try to take example, I'm taking two particles just to make a simple. If one particle is moving towards right, another particle is moving towards left, as they're at the same temperature, so they will have, because the mass is same, so they should have same kinetic energy. So in that case, they should have the same magnitude of the velocity. But if one is positive, the other one should be negative. It's up to you. If left hand side is positive, right is negative. If right is positive, left will be negative. But when I take an average velocity here, so average, it will be plus v, then the second one is minus v and divided by 2, because I'm taking two values. So it will be v minus v divided by 2, and v minus v is 0. So 0 divided by 2, I should get 0. The kinetic energy is 0. So if kinetic energy is 0, it means the particles are not moving. But in practical, the particles are moving. So that is why if I try to take an average velocity, I cannot take an average velocity. Why I cannot take an average velocity? Because the particles are moving randomly. So if one particle move right, so if one is moving towards left, so average of the particle which are moving towards right and left will be 0. But that does not support an idea that particles are moving and the average velocity is 0. So how to overcome this? So what we do in that case, what we take root mean square speed, actually, or square velocity. So root mean square velocity. So what is done? The name is root mean square, but what is done? First we take a square, then we take a mean, and then we take a root. Example, if two particles are there, they're moving in opposite direction. So I will not take average, I will take root mean square velocity. So what is the meaning? Like if one is moving with plus v, other one is moving with minus v. So what is the meaning of root mean square? So first we take square. So I'll take a square of this plus v, and I will take the square of minus v. Because when I take square of positive number is positive, but square of negative number is also positive. So both values will become positive. So that is v square, that is also v square. Then we take an average. How to take an average? So v square plus v square divided by 2. If there are three velocities, then v square, v square, v square divided by 3. So then we take an average, like the sum of the velocities divided by total. So v square plus v square divided by 2. But because we took a square first, so how we can reverse the effect of the square, or what is the reciprocal or inverse of this square? That is root. So then we will take a root. And what we call this speed, we call that as VRMS. So when we are substituting the value, like when we are finding the kinetic energy of the gas molecule, we say half mv square. But what we substitute in this place of v, we do not substitute the average velocity. What we substitute v RMS, which means root mean square speed. Is it clear? Why we are not substituting the average velocity? Because average velocity might be zero. Possibility is there. That's why we take a root mean square speed. That root mean square speed cannot be zero. It will have a value. It will can be zero if the particles are not moving, but if particles are moving, the root mean square speed cannot be zero. Is it clear? So the formula which relate the kinetic energy and the temperature of the gas that the kinetic energy of the gas is equal to 3 by 2 kT, where this is kinetic energy. The derivation of this formula is actually derived, but you don't have to go through the derivation. I can derive this formula as well. But for course outline, you should understand the fact that kinetic energy of the particle, and that is the kinetic energy of the gas molecules. Basically, this is based on the gas law, so it is applicable for gas particle, not about the solid or liquid. So kinetic energy is equals to 3 by 2 kT. And what is K? K is Boltzmann constant. And T is the absolute temperature, or temperature in Kelvin. And this formula shows that kinetic energy and temperature are directly proportional, because 3 by 2, it's a constant number, K is constant. So this, for if I replace the constant and equal to, I will replace with the proportionality sign. So kinetic energy is proportional to temperature. And we know kinetic energy of a gas is half mv square. So it will be half mv square. But what is V here? V is Vrms. What is the meaning of Vrms? It means root mean square speed. And that is equals to 3 by 2 kT. So this is a formula which relate the root mean square speed with the temperature. So from this formula, what you can say, it means the root mean square speed square is proportional to temperature. Means if I double the speed, what will happen? The temperature will increase by 4. If I triple the speed, the temperature will increase by factor 9. So vary with a square. Is it clear? The relation between the temperature and the kinetic energy of the gas molecules.